Gervais Restaurant, authentic French cuisine in Silicon Valley.
I've had a couple of exciting days. I just got in late last night from Oahu and experienced had a very interesting experience on the 15th floor of a building there. I thought I was escaping California, so I'm shaken, not stirred or something. And this morning is, I guess, what was his name? Neil? We were dedicating the SETI Institute on the board of trustees there, dedicating the Carl Sagan Center, and Carl was also on the board at the time of his death, and his widow Ann Bruin was there to dedicate the center, and along with Scott Hubbard, who's the exiting director at NASA Ames and is now Carl Sagan chair of the center.
So anyway. Just to be clear about Greg's priorities, he warned me this morning. He said, "I will likely be late."
But it's a very exciting thing. So I'm here to talk about this. For people who engineers in Sun, I drive people crazy with my thought experiments, which are they're really powerful ways to go about things, particularly with these kinds of rates of change. And one of the ones I've tortured people with over the years are look at all the servers and storage systems we make at Sun. And I want you to, the thought experiment is, what if we were the only company buying them? Okay, so this is, for example, we're putting up grids and provisioning out the cycles and selling cycles. We were fundamentally responsible for computing. So if that were the case, what would we build? Right, would we build exactly what you see here as an example? Would you build that range of things? If there's actually a whole lot of this stuff, the answer is no. It would look different. It wouldn't be the same probably kind of breadth in the product line. There'd be more focus on this place, and this place. There'd be things like would you have PVD players and nice shiny bezels and USB ports and all this stuff coming out of the front. And you can go through those kinds of thought experiments, which are really ones that are driven towards what's essential here. How do you get really efficient at designing and delivering and provisioning computing? So if you go back and just if you go back and look at this slide and really take any of these companies and for an aggregate, something like ExxonMobil or Citigroup, and look at, say, in those cases, the high performance computing component. But if you look at that, these are buyers that are actually very sophisticated technically. They have also a very refined sense and metric about what's important and the efficiency at which they deliver their infrastructure and their computing. And it goes to, why does power become the second most important thing to someone? That's because a whole lot of other things were worked on. And it's not the price of software. You notice many of these companies up here are basically on free software or on community-built distributions. They look for efficiencies in that way, but also efficiencies in the composition of the systems as you scale out. So there's and just reflect upon that for a minute. So you kind of get to the next level question, and you see this hyperscale, because that's really what's happening here. These are the things where you get to the, gosh, does Google have 1 million servers now, and what is Microsoft going to do to, sort of put their billions of dollars of capital down to build that out, and what is life really going to look like there? You got to go back to basic assumptions, and the basic assumptions that went into the design of the black box were ones that were grounded in looking at the needs of that line and how do you get exceptionally efficient, reactive, be able to build things at at rates that are far more consistent with the reaction times of these businesses. And that's, I think, the context that I want to give to you here. I firmly believe that this kind of code design, and by code design I mean taking the physics of the environment, the server and storage systems, the networking that go with it, and do that as a single design exercise is going to be the way. In fact, I'll be categorical about it in these lines. It's the only way people will survive along these lines and stay competitive. And again, to emphasize what John said, doesn't mean that data centers go away. We're not saying that at all, because it's a big portfolio of things. But when you're driving towards that efficient end of the spectrum, that's what it's about. So I'm going to kind of step through what's in here and what the set of innovations are. But let me also warm you up a bit with another set of questions.
Gervais Restaurant, authentic French cuisine in Silicon Valley.
And they're a bit rhetorical. So question number one for you is, why do we build data centers? Just kind of mull over that. Why do we do that? Right? And say, okay, maybe we do it because putting multiple things in one place, or servers or storage or whatever you have, gets you to points of administration that scale. You get to aggregate things like your service infrastructure, bandwidth, network, and all that. Great. Lovely. Why do we build machine rooms? Decided we're going to put data centers and concentrate things nearby each other. Why do we build machine rooms the way we build them? Okay. Well, that's actually historical. Okay? We built machine rooms as places where people and machines can cohabitate. And why did we do that? Because for many years, people needed to hang the tapes on the tape drives and clean the chat out of the chat drawer and interact and operate the equipment. And it was that relationship between the two of them. And so you get into this constraint that as you build data centers, you're building things that are both things that are satisfying the constraints of the machines and the ones that are satisfying the constraints of people. So kind of silicon and carbon, and you've got to make those both happy together. And essentially what's happening is power densities, despite all of the, and for good reasons, power densities are going through an enormous acceleration. And you look at racks of equipment here. These are very fuel efficient designs, so to speak. But there's 10,000 watts accumulated in that rack, and it's going to go to 15 and 20 and 25,000 because the density actually lets you get superior connectivity and networking among those components, even when you drive them with very, very efficient components. So that's where we basically ended up. The most important single assumption in here was this is a space that's designed for machines and riding on the trends towards lights out management and virtualization. So let me step you through about what's in there and why it's in there. And I'm going to skip over all of the words and things that are words. Okay, so here's the physical details. As we've probably said many times to you, you start with a standard 20-foot container, and we're able to, even in 20 feet, get 8 racks along the side and in very high power racks at that, and you'll see why that is. Normally these shipping containers cost about I think about $3,000. Yeah, but if you get another set of doors put on them, so yeah, maybe we get the extra set of doors free. So these are things that are made in very high volume. They're actually beautiful. They're precision welded. There's some place in China that makes 90% of the world's shipping containers. But basically, one of these really happy coincidences, and if people read Levinson's book, I strongly urge you to read it. It's delightful. How all the different, why does a container look the way that it does in its size, and it was really to satisfy a whole bunch of constraints, not the least of which, you know, what would fit on a truck and be regulated by interstate commerce properly. But all of that ended up with the ability that you could put, as you look in here, and I'll just talk against the top here, is that if you look down at the top, there's a row of racks like this and a row of racks like this. And there's space in the middle, just enough space in the middle for a service aisle as you need it. I don't know, does this tilt on its side easily? So.
Gervais Restaurant, authentic French cuisine in Silicon Valley.
Take that off and maybe even be on it. Yeah, okay. But so you can see essentially in here are, looking down from the top, are the 8 racks, sort of the service aisle in the middle, and importantly, if you really want to understand this innovation, it is that between each rack is a set of heat exchangers, just standard water-cooled systems, and there's a recirculating air path that just is this, you know, take the air and keep moving it around and around and around in here, front to back, off of each of the racks. Now, if you did that for any length of time, this would melt, right? So it's like 200 kilowatts. That's, you know, take 200 of your air dryers and turn them on and put them in a room and run away. And so the trick is, as the air exits each rack and before it goes into the next one, there's a heat exchanger. And that heat exchanger takes the hot air that's exited and cools it down and makes it suitable for it. There are tremendous kind of benefits that you get out of this, which is that this is a closed air path, so it's sealed, right? It's the air that's in here is the air that's in it. So, you know, there aren't big humidity and particulate filtration concerns. You can imagine things like fire suppression are a lot easier to deal with in environments like this. So there are, you will see as we walk through things, you'll see some air filtering and some humidity control, but that's really lightweight stuff. It's not necessarily to kind of keep this thing going. So let me move on, and we'll go back and forth the picture, and then the big thing is that we're going to go tour it. We do some mechanical enhancements of these things, like putting in a decent floor and some structural reinforcement. And this is the kind of the magic of the whole thing here. This is the airflow that I was talking about. That here's a rack, and kind of the front of the rack here, and the output here, and the air flows across the rack. It's actually cooled down by the heat exchanger and is ready for the next one. Okay. And then there's a closed plenum in here, so it just keeps going round and around and around and around. It's actually surprisingly efficient. And one thing that you'll notice is that, well, there are generators and things that are out there. It's not nearly as loud as you would think it would be. Okay. And partly this is because, well, we're going to have it open, so it would be louder. But when the box is closed, it just kind of works because the air just keeps going. You're not accelerating and decelerating the air. It's extremely efficient, and that's one of the leading forms of the power savings that are there. And what I was saying about, you know, how the standards gods were sort of smiling is that this, you know, you can fit a row here and a row here, and there's enough room to slide one of these racks out. And there's a special tool we have to do that while maintaining all of the connections in and you can see along the side here the heat exchanger. These are really standard vanilla heat exchangers, car radiators basically. And you also see, you look in decal, there are lots of attention to things like flex couplings and shock mounts and the like. This is to be transported with fully configured and wired, and you have to sort of account for what happens during that transport. And we have moved it around because one thing that you might want to worry about is as you move it around, you can get great air ride systems and the like, and keep the stress effective. We drove the last trip up to the Bay Area. We got 1.5 Gs or something. Yeah, 1.5, 2 Gs. We were all happy. We had unloaded it. We loaded it back up. We did great. Got back down to the shop in Burbank. and it was getting unloaded, and it got dropped. But, 6 inches or 6 inches, which was our, was going to be that, you schedule it out in a few months, you're going to do the drop tests, and what happens if it gets dropped. And we popped up to how many Gs on the drop? It was like 8 Gs. Yeah, 8 Gs on everything worked just great. It's all designed for that. And as you notice, because it's exactly what you have to worry about, is how these things are handled and dropped. And you'll see things like shock isolators on the top. I don't know if this is the most recent design of that. Power distribution, dual redundant 208 feeds. And this is really the simplicity of it, which is, you add water, bandwidth, and power, and you're done. Right? That's, in some sense, you say, why now? How could you? Because certainly putting things in containers has been around a long time, and particularly military applications, people have done this a lot. But what's the set of things that come together that you really say this is actually an efficient way to do it, and you want to do it mainstream? As I said, things about power densities increasing start to make having this kind of real estate inside a container the right thing, but also because of the network, right? People have no functional fixedness anymore that, oh, well, what if I need 2 of these, or if we're really designing this 10 or 100 containers, well, you network them together. I mean, that's not, I'm getting hooked. And so as you look at the bottom, you'll see things like shock isolation and like the rest. So go take a look at those things and hear a bunch of outrageous marketing. One thing that I think we haven't even said in here, but just to make it really clear, I feel very passionate about this, as does Dave Douglas, who's our VP of Eco Responsibility. This is a full life cycle concept. And one of the charms of this is you have a worldwide infrastructure to move these things around. So you can think about service in a very different way if you want. One thing, the promise that we make with it is at the end of life, we will take it back. And we will go deal with and recycle and remanufacture everything that's inside that box. So just move it away. You get it without any cardboard packaging or peanuts or styrofoam or anything like that. Right? And we'll take it back and do all the right stuff with it. And we have an exceptional track record in that, just to blow our own horn a little bit. But far less than 5% of what we take back in our equipment ends up in the waste stream. And we really recover plastics, metals, we remanufacture systems, we have just an exceptional program in that. And I think that's a really important thing here too, is to be responsible. So I am done.
Gervais Restaurant, authentic French cuisine in Silicon Valley.